and welcome to a new episode of the Plan C Ocean Interventions to Address Climate Change podcast. As always, I'm your host, Will Burns. I'm co-executive director of the Institute for Responsible Carbon Removal at American University, and I'm joined by my co-host, Anna Madlener, who is senior manager for MRV at the Carbon to Sea initiative. Hi, Anna.
Hi, Will. Good morning.
Hi. So today we're focusing on how to study the environmental safety and efficiency of ocean alkalinity enhancement through the lens of the Ocean Alk-Align Research Consortium, which is a research project designed to investigate the efficiency and durability, environmental safety, and monitoring, reporting, and verification requirements of ocean alkalinity enhancement. We're joined on today's episode by three postdoctoral researchers from the consortium: Leila Kittu, Giulia Faucher, and Charly Moras, who are all engaged in laboratory and Mesocosm studies of ocean alkalinity enhancement. Together, we're hoping to unpack how to design good environmental studies, what Mesocosm experiments can tell us and what they can't tell us, and which processes really drive how much carbon the ocean can lock away and for how long. What are you looking forward to in the episode, Anna?
I'm very excited to talk to these three fantastic researchers. I had the pleasure of meeting a number of them before we actually visited even the research site in Kiel last fall. And one of the things that sort of stood out to me then, we were watching or observing them doing Mesocosm studies in Kiel. One of the things that stood out to me was that that's something we talk about a lot and reference a lot in sort of other episodes. The fact that there is foundational research or that there's evidence from Mesocosm studies that, something is true or not true in OAE. And I think that many people don't know what it takes necessarily to conduct a Mesocosm experiment, what that might even be. And so I'm really looking forward to unpack those mechanistic aspects of this foundational research. And yeah, we should also say that it's just a subset of the Alk-Align group. It's a research project conducted at 5 different institutions. So this is just a small glimpse, but a mighty glimpse into all of the work that they're doing. How about you, Will?
Yeah, I'm interested in unpacking the role of Mesocosm studies also in more detail than we have in the past. And I'm interested in determining whether the researchers found substantial differences in organism responses across the test regions that they were focused on and what the implications of that might be for wide-scale deployment of OAE in the future.
Cool. All right, shall we bring them in to discuss more of that?
Sounds great. Okay, so let's start with introductions, and we'll start with Giulia. And could you also introduce the Alk-Align project a bit for us?
Yes. First of all, thank you very much for inviting us. I think we are all very happy to share our research. My name is Giulia Faucher. I am a postdoc at GEOMA, which is Ocean Institute in Germany, based in Kiel, so on the Baltic. And my research is focused, I might say that I am a phytoplankton lover. So this is the core of my research. And in ocean alkalinity enhancement, I mainly try to assess how to apply ocean alkalinity enhancement in the safest way possible for the ecosystem. And yes, I'm part of Ocean Alk-Align. I'm also a Marie Curie Fellow with part of my work. And Ocean Alk-Align is an international project where different groups work together. We are coming from not only different countries, but different continents. So the lead person is Katja Fennell from Dalhousie University in Canada. But there are other groups in Tasmania, in Australia, in Germany. And we try to work at different level, looking at efficiency, but also durability of ocean alkalinity enhancement, environmental impact, and also MRV. So we kind of work together at different levels to try to find a way to reply to the question if OAE is actually possible to be applied and to be deployed at a larger scale.
Yeah, hi everyone. Thanks Anna, thanks Will for having us today. I'm Charly Moras. I'm a postdoctoral research associate at the University of Hamburg in Germany, so kind of a neighbor of where Giulia is working as of now. And I completed my PhD about 2 years ago now in Australia, where I worked on ocean alkalinity enhancement and the dissolution of different materials, basically for the carbon dioxide removal strategy. And since I moved to Hamburg, we've been working a lot on dissolution of materials, understanding how to apply ocean alkalinity enhancement, trying to understand thresholds, and see basically how feasible it is from a carbon chemistry point of view. And of course, we had the opportunity to collaborate a lot with Giulia, Leila, and the greater group at the Geoma on several field campaigns.
Hi, everyone. Hi, Anna. Hi, Will. Thanks so much for having us. Just a little bit about myself. My name is Leila Kittu, and I'm a researcher, specifically a marine biogeochemist at Geomar Helmholtz Center for Ocean Research in Germany. And yeah, I'm here today because for the past 2 years, I have been working on environmental impacts of ocean alkalinity enhancement, and I'm excited for this discussion. Thank you.
Great. Thanks for the introductions. We're super excited to have you all here. And Leila, I wanna kick it off with a bit of a high-level philosophical question, I suppose. We often talk about this concept of environmental safety of ocean alkalinity enhancement, and I'm wondering if you want to share broadly how you approach the design of research around this topic.
Yeah, thanks so much for the question. I think so. When we think about environmental safety and how to design experiments, we have to go back to the fundamental question, which is the basic idea of what ocean alkalinity enhancement exactly is. And so when we think about designing experiments, I first of all have to say that it is one of the biggest challenges, and that's because the ocean is huge and it's incredibly complex, and ocean alkalinity enhancement will probably operate on scales we've never tested before. So the way we tackle this is we try to break down the concept of alkalinity into manageable pieces, at least from an ecological perspective. And we really simply start by asking, if we add alkalinity, what actually changes in seawater, right? So things like pH increase, or the concentration of CO2 or carbon dioxide decreases in some cases. And so we actually change the seawater carbon chemistry. And therefore, we expect that marine organisms will react to these changes. So that's the basic idea. We need to understand what alkalinity actually does to seawater. And so we design the experiments at multiple scales. And in our work, we've mostly used a phased approach. That means we start small in the lab, where we have everything controlled, and we test or simulate different minerals, for example, which are relevant for the application of alkalinity enhancement. And then we start by testing at individual levels. So that means, for example, how single species or a specific specific process like calcification will actually respond to ocean alkalinity enhancement. And the idea of using this phased approach is that when we start at a small scale, we gain a mechanistic understanding of what specific organisms are sensitive, or at what concentrations those impacts are actually seen. And then once we understand the basics, we start to move on into more complex setups, such as microcosms or mesocosms. So microcosms are just a little bit smaller. You have about 60 liters of water, while mesocosms are much, much larger. And the idea here is that we start to include multiple species. So we go from a single species to multiple species, where we try to catch or watch how communities or plankton communities will actually respond to seawater changes. And at each step, we set clear questions and kind of measurable endpoints. What I mean is that that might be things like species abundances, which is an endpoint. So we manipulate the seawater and we see how do those abundances actually change, or how do the growth of certain species actually change. And that tells us whether the system is actually being impacted or not. So one important feature of our experiment so far, what we've done in our experimental design, we've tried to use alkalinity gradients. That is, we start from low doses to actually very high doses, so that we can see not just if things are changing, but when they start to change. And that's really important. And that helps us to identify things like thresholds or nonlinear responses that we might not able to capture in the real world. So in a nutshell, studying environmental safety in OAEs is really about breaking down the problem into manageable pieces and then scaling up step by step.
That's super interesting. I love that. Thank you. You already alluded to it, but I wonder if you want to share a little bit more about specific hypotheses that sort of guide your research the past 4 or 5 years. And you mentioned, for example, that you, I guess, anticipate that there's perhaps varying levels of alkalinity where varying species start to change. Curious if you want to share a bit more about those hypotheses.
Yeah, so we've started doing research on ocean alkalinity enhancement. I think we're about 4 years in, if I'm not mistaken. And the key questions that have really shaped our research, there are many, but they really come from trying to understand not just if biology responds to ocean alkalinity enhancement, but how and under what conditions. And so if I would highlight, for example, a few questions that we've or hypotheses that have shaped our research, the first one it's quite simple, but it opens a very huge door, and that is how biology responds when you increase alkalinity, and whether it matters how that alkalinity is actually increased. So we have 2 scenarios that we've studied so far, which are using an equilibrated alkaline solution. That means basically that the alkaline solution has actually equilibrated with the atmosphere, versus if you would add an alkalinity solution that has not equilibrated, so the intended CO2 has not actually been taken up. And so those 2 scenarios, for example, are things that could inform about the environmental safety of how we should apply alkalinity in a safe way. And that's because in real OAE scenarios, sometimes the added alkalinity will make solid or will mix much slowly, meaning the water might temporarily experience really high pH or carbonic chemistry shift. And it's important to understand how organisms react, And maybe the second question that we've also tackled is, are any of these biological responses, for example, predictable? And in other words, are there clear thresholds where we start seeing changes, or do organisms actually adapt or recover once conditions kind of go back to optimal? So these are some of the questions that we've currently tackled, yeah.
And somewhat related to that, when you do see changes in a system, how do you decide whether to call it an impact? It's an impact can be positive or negative. So I'm curious, how do you categorize or sort of analyze these responses?
Yeah, that's the fundamental question of our research, right? Trying to decipher is what we see really an impact? Does it really make sense from an ecological perspective or not? And we go about it by thinking in different ways. So one is that we ask simple questions like, is this change actually caused by the alkalinity addition? Right, and to discern this, we employ different tools. For example, we look at controls. So controls are basically same experiments where we didn't change alkalinity. We also, as I said earlier, we've used in most cases alkalinity gradients, and so we check along that gradient to see whether the response scales with the treatment of alkalinity that we've actually applied. And if the change doesn't track the gradient, or actually we also see a similar response in the controls, then it's more probably that it's not an OAE effect, and there's some other confounding variables, right? The second step is also the magnitude of the change, right? How big is the change that we see in a certain plankton community, and also how persistent is that change? And this is because some responses are actually very small, and they're actually within like natural variability. So one needs to be careful about calling those impacts, because you actually need to quantify that change in a certain response, But if a change is large, or it's consistent across the gradient that we're looking at, or even persists after certain conditions, then we start to think of it as a potential impact, right? And we start to dig deeper into it. The other aspect is about characterizing the change. So you might have things like, is it a direct impact of the alkalinity treatment that we've added? And this has to do with not just the alkalinity, but several components of the seawater chemistry that we change, things like pH that are actually changing, or concentration of CO2 that might be relevant for phytoplankton, for example. And so we start to characterize those changes as direct if they are directly reducing things like growth, or they could also be indirect in a case where phytoplankton is actually impacted directly, but because it's eaten by a zooplankton, and we actually see that the zooplankton is affected somehow because they're eating a phytoplankton that is also affected, then that would constitute an indirect impact, right? So those are the kind of ways that we try to decipher what is really an impact and what is not. So it's really about the magnitude, but also the ecological application of it. Does it really matter for the ecosystem? Right?
Awesome. Thank you so much for that overview. I want to hand it over to Will to share more about and ask more about the mesocosms.
So, Giulia, why are mesocosms particularly useful for OAE research compared with, say, purely lab work or field trials?
I would say that mesocosm are experimental enclosure, but they are the most similar one we can get to compared to, a natural system, because they are deployed in the water. So they have very similar light conditions, temperature condition, and then we enclose a natural community. And they are very useful because we look at, we enclose a community like an almost not disturbed plankton community. And we can look at different levels in the trophic level. We can look at the interaction from microbes up to, with the very, very large mesocosm, up to the fish larvae, so the highest trophic level. And we can look at how the ecosystem responds to the perturbation induced by ocean alkalinity enhancement, but also if the system is able to, how resilient the system is. And as Leila mentioned before, somehow we can also look at if, one change that we see at the very beginning of the experiment goes on, or if it's just transient, if there is some kind of compensation. So they're really a perfect tool for gaining lots of information at different trophic level and how these interact one with each other. And also, I would say that in this time where it's quite hard to get a permit for doing field trials, the mesocosm are, of course, we follow some rules and protocols, but they are very safe because this is just water that is enclosed in these bags. But this water that we manipulate is not in contact with, the water mass outside. So it's very safe. And therefore, we just have to be careful when we finish the experiment to follow the protocol to release this water, but we are not modifying anything outside. And then it's also true that these studies are, for an institute, they are quite expensive. But so we spend lots of our resources for performing this experiment, but they're definitely much cheaper compared to field trials.
Mm-hmm. And what's the flip side of this? What are the main limitations of these studies? What can't they tell us?
Of course, since they are enclosures, by definition, we cannot gain information about mixing and dilution. So this is the main difference compared to field experiment. And and as Leila said before, we normally work with gradient. So we have a control and then we have a progressive increase in alkalinity. This is how in the last year we are doing our experimental design. And so we use gradient to somehow, identify when we see some changes, but it's not like looking at dilution and mixing, and it's a very stable system. Also true that since we enclose this water mass for some time, so with the offshore mesocosm, our experiment, they last 2 months or so, and with the onshore mesocosm around 1 month. Sometimes you can get away from reality because it's the same body of water in that you're looking at. So maybe some processes are enhanced because of that, because the zooplankton is there, is eating the same phytoplankton, and maybe in a natural context they will have a chance to move around and so on. So this, I guess, is the main limitation of the mesocosm. But you have to consider that is an experimental setup. It's not what is happening naturally in nature. So it's a compromise that we have to take into account.
Yeah, and a really important compromise on the way to a field trial, right? Like very important groundstone to sort of lay. I want to shift from the environmental safety to the efficiency aspect of mesocosm studies. And Charly, this is obviously your arena. Before we sort of dive a bit deeper into your work, specifically with the Alk-Align group, I wonder if you can sort of lay out the main efficiency drivers of OAE, so the big levers that matter for how much carbon is actually removed on a, I suppose, more physical and chemical aspect.
Thanks, Anna. Yeah, I mean, it's good because it follows a little bit with what Giulia was discussing about the mesocosms and the limitations compared to open oceans. I mean, currently the concept of efficiency mostly kind of like stems from the amount of CO2 removed per amount of material added, basically. Like everyone is interested in how many tons of CO2 is removed per ton of material. And this is, I think, the general understanding of what efficiency stands for. But with all the work that has gone into OE over the past 5 years, there's more concept and ideas that came out about efficiency, and that goes from, there's different groups of efficiency, let's put it that way, where mainly loss of efficiency we will talk about in the way that it's not just about how much material has been added, but rather how much of the material that has been added, the alkalinity that has been generated, remains in contact with the atmosphere for capture. And in those pathways, we have, of course, everything that has to do with the material that may not be pure, might be only 99, 98%, which means that it also will decrease that overall efficiency. Then you run into the situation where you put it in the ocean, you wonder whether it actually has fully dissolved. Did it actually, for whatever reason, thermodynamically only dissolve at 90%? So you lose already a bit of potential. You have the sinking problem, which is something that we don't have in the mesocosm because they are closed. That's why I was like, it's a cool link. Then you run into the other thing where talking about dilution and horizontal mixing or subduction, it's all about how long does that alkalinity stays in the surface to basically exchange with the CO2 and capture that CO2. And then you have that last efficiency that was basically most of what we've done over the past few years, which is understanding what we now kind of frame as the stability of alkalinity, which is, does it stay dissolved in water or is it lost to secondary mineral precipitation, for example? So it's not just anymore, I have added 1 ton of whatever material and I'm expecting 1 ton of CO2 captured. It is actually, I have did that in an ideal scenario would be 1 ton, but realistically what is happening? And there's different little pathways of efficiency losses, let's put it that way.
Great. And so in your work with the mesocosms, what have you been looking at so far?
Well, so the past few years, we the mesocosm, we mostly look at the role of different materials or how different material could have an effect on living organisms, essentially. And more recently, so over the past 2 years, we've been interested in actually using solid feedstock. So it really started with not a safe approach, but we used equilibrated approach, liquid feedstocks, which are easy to manipulate, easy to mix. And there's very few things that can go wrong in the way that whenever you're going to add 1 kilogram of feedstock, you will have most likely 1 kilogram of alkalinity generation if it is a 1-to-1 ratio. Over the past 2 years, basically, the last 2 mesocosm campaign, we're looking at solid feedstock. So you bring into that dimension, or into that context, the dimension of sinking and the dimension of potential precipitation, like that formation of secondary mineral phases. So it is always present when we have liquid or solid, but it's true that over the past few years, that's what we've been looking at, whether, when we've expected, I don't know, like that 10 gram would have made a difference. Maybe we only measure that actually 7 grams made the difference, and trying to understand where are those missing points going, basically.
So super interesting. Sort of in that vein, over the past few years, was there anything that has surprised you about these efficiency drivers, either from the models, perhaps, that you've been working with as well, or from the experiments themselves?
From a personal point of view, like the one thing that really surprised me was that secondary mineral precipitation, because, when we started our PhD, because we started at the same time with Leila, about the literature available about OAE was quite limited and was mostly modeling studies that were very encouraging, had tremendous numbers of carbon capture potential. It was really an exciting stuff, but no one really ever put the rock in the water and just assumed that things were happening there. And so one surprise was that actually it's not as easy as just pouring, particles in the ocean. There's a whole dimension to it, which is, does it dissolve? Does it sink? Does it co-precipitate? And what's happening? So that was probably the most surprising aspect of it.
Cool. And how do you then connect what you see in the Mesocosm studies to the real world application of OAE and sort of the design of field trials potentially as well? Is there anything that really stood out to you so far where you thought, I want to make sure that everybody knows about this because it's relevant for non-Mesocosm implementation?
Yeah. I've always seen it where you have, the difference in between a lab scale study and a Mesocosm study is quite similar to what a Mesocosm is to a field trial. In the end of the day, it's essentially just, I should not downgrade Mesocosm to that, but it's just basically one big beaker that we put in situ. And instead of having it in a water bath, we have the ocean. So it is a very similar approach. And so it was quite interesting because the research that we did, so we were quite lucky to be invited by the Guioma and the Guioma team to join them on Mesocosms, especially for example, the University of Hamburg, or the group I work with, has been invited since 2021. And the few research that we did early on kind of helped later on design the next Mesocosm study. So what we saw on the side experiments while they were doing Mesocosm study led to basically designing the next one. So I can clearly, see that link that is happening on one way from lab scale to Mesocosm scale. So I can definitely see the link from Mesocosm scale to field trials as well. And what is nice is that what we see in the lab is less likely to happen in a Mesocosm already, given that we have dilution, we have a lot of interactions with biology that makes a big difference. So most of the processes that we see in the lab are less likely to happen in a Mesocosm experiment, which also hint towards the fact that what we would see in a Mesocosm is less likely to happen in field trial, because you bring that dimension of, horizontal, vertical mixing, CO2 exchange that would be potentially higher because there's no wall around the ocean. So that's basically the kind of the flow that I've always seen, and that kind of makes the extrapolation or basically the thinking of how they link together quite interesting.
Yeah, I can imagine also that if something doesn't happen in a Mesocosm study, would you say that you can be safe to assume that it won't happen in the field trial, and sort of the opposite?
Yeah, or you would say that it would less likely happen, unlikely happen. I would say I never want to say yes or no to because who knows, but realistically, it's unlikely to happen. We've seen it also with the bigger Mesocosms where we actually have some more room to do stuff that are, and at least the effects that we see in the bigger ones are not the same than the smaller ones. And that could potentially be because it's more concentrated as well, the same way we see when we have experiment run in a small beaker compared to a big beaker. There's this pressure of the vessel and the environment that is different. So it is easy to think that way, that what we see in the Mesocosms is less likely to happen in open ocean.
Mm-hmm. And has there been, I guess I'm sort of rephrasing my previous question a bit, but have there been any sort of early conclusions or indicators for specific feedstocks, solid feedstocks that you've added, where you can sort of already draw some conclusions, or where you have some hypotheses for how they should be applied in field trials or should not be applied in field trials?
I mean, an easy answer would be yes. I don't want to get anyone on my back for standing for one feedstock over the other, but it's true that it all comes to how you implement it, right? So one feedstock may be suitable for a coastal application, but won't be suitable for open ocean. I can think of any feedstock that takes longer to dissolve than it takes to sink should not be considered for open ocean. The same way the other way around, where if there is a feedstock that, that could be, a lot of turbidity, may not be considered in a place too concentrated or a basin, but probably somewhere where the turbidity can be diluted quickly. And there's been like a lot of research with plenty of feedstock. I can think, just in my case, I probably said it already, like 8, 6, 7 different ones. So that gives already a broad spectrum of feedstocks. And overall, the one that are the one that come back the most often, let's put it that way, would be mostly hydroxide. So anything that has to do with sodium hydroxide, calcium hydroxide, magnesium hydroxide, which are fast dissolving, which mean that they're probably suitable for open ocean. One could consider also in a coastal setting or in a reactor with a discharge, a slurry, and so on. And they've been the one that are the more understood and considered as of now.
Yeah, very, very interesting. I think it's going to be valuable to see more outcomes from that. We, in our previous episode, talked with Phil Renforth and Meindert van der Speek about their LCA, TEA, life cycle assessment and techno-economic assessment framework, that is. And anecdote, I think we mentioned in that episode that they identified 54 variations of OAE pathways, right? Like from point of addition, method of addition, type of feedstock, and there was one other category that I forget now. But you're already alluding to something similar, right? There's so many considerations about where and how to do OAE if we want to do it. And so, yeah, very curious to hear more about those outcomes eventually.
Let's circle back a bit and talk about some of the environmental findings from these studies. So, Giulia, looking back over roughly the last 5 years, what are some of the main insights on the environmental safety of OAE that you've gleaned from the last 5 Mesocosm campaigns?
I think that there are, three things that I learned in the last experiment, which I think it's already quite a lot. First of all, the first experiment that our group at Geoma has done was in Gran Canaria in 2021. And as someone mentioned before, it was an equilibrated ocean alkalinity enhancement approach. So we introduced inside our Mesocosm a solution that was already equilibrated, and therefore the organisms were not subjected to extreme carbonate chemistry conditions in terms of pH, or they were not experiencing CO2 limitations. And in this experiment, what came out from the papers that has been already published is that there's almost no impact or very limited impact on the organisms for a very short time. And so it's quite promising. Let's say that an equilibrated OAE approach should not, be negative for the ecosystem. And this, I think, is a first lesson. The second lesson is a bit more complicated. And we learned that there are many differences when you perform an experiment in terms of location and time. So it matters a lot depending on the environmental conditions, like temperature, for example, or the community, of course, that is enclosed in our experiment. The outcome could be different. But it's not only that. Last year, within the project Ocean Alk-Align, our group performed 3 experiments in Kiel, so here at home somehow, at 3 different seasons, one in spring, one in summer, and one in autumn. We are still looking at the data, but the idea was to apply the same experimental design in different conditions that were different condition of nutrients, for example, because it's the natural, cycle here in Kiel. We have high nutrient in spring and then low nutrient in summer and in autumn before the nutrients are coming back again. And the temperature was, of course, very different. In spring, the water temperature was around 6 degrees, and then it was much higher in summer, but also in autumn. And we apply the same experimental design, and we expect to obtain very similar results. But there are some differences. I'm not going to say much about it because, as I said, we are still looking at the data. But it's kind of, something important to keep in mind that it is not that if you apply the same approach in different locations or at different time, the outcome is going to be the same. And then the third thing that I learned, it's about high trophic level, because nowadays there's lots of, initiative towards looking at high trophic level fish, for example, fish in particular. And they are new studies and new, yes, as I said, initiative. But I think that these comes from one of our Mesocosm study that we did in Bergen in 2022. And there is this paper by one of our colleagues, Sylvan Goldenberg, 2024, in which for the first time he's talking about fish, because we introduced in our Mesocosm fish larvae. And before that, all the research was, in the direction of phytoplankton up to zooplankton. So it was really the first time that someone kind of say, hey, we should also consider high trophic level because, it's not only about the low ones. So I think these are the three main lessons that I learned in the last 5 years.
Yeah. I think that focus on higher trophic levels is going to be extremely important, obviously, for a lot of stakeholders, right? That might ultimately be engaged in determining whether we move forward. So that's very interesting. What makes this mesocosm work in this context of environmental impacts particularly challenging? Is it about endpoints or the higher trophic levels that we talked about, or timescales? What creates kind of intrinsic, if there are intrinsic limitations to the kind of conclusions that you can draw about environmental impacts?
I mean, high trophic level for sure, because you can add, as I said, fish larvae inside our mesocosms, only, by the way, on the large one. So the one that contains around 30 to 60 cubic meter of water. So the offshore mesocosms. But it's still limited, right? Because it's fish larvae. It's always very complicated. There's always lots of big question marks about if it's going to work or not. So there are different setup that should be used, which are not the mesocosm, to understand what is, also the physiological response of fish. Is it a matter of change in pH or presence of particles in the water or anything else? So for sure, for high trophic level, mesocosm can be, not enough. And then I would say that with the mesocosm can give us information about short-term or middle-term responses, because they cannot last too long, because we have a certain volume, and also because it's just the same volume of water. So you're just looking at the same thing somehow. So the small mesocosm, the experiment, they last around a month. With the big one, you can go up to 2 months maybe. And so you can just gain information about short and middle term. And then if you want to understand if OAE might impact an ecosystem on a longer term, you have to think about different approaches. So these, I think, are the two main limitations.
That's a very important point. I think, again, similarly to Charly, pointing to the fact that we need to always transition between these different stages, and you're learning important things that will then sort of inform the next one. I want to work it back one scale, actually, in the opposite direction, and talk about the OAE PIP exercises that, Leila, you are currently running. You are in Kenya as we speak, running experiments linked to the OAE PIP exercise, which listeners may actually remember from our episode with Tyler Cyranek and Lydia Kapsenberg. He briefly introduced these. Do you want to quickly share more about what you're doing and how these experiments fit into the broader picture here?
Yeah, I can do that. So maybe just shortly, OAE PEEP stands for Ocean Alkalinity Enhancement Pelagic Impact Intercomparison Project. And it's basically a globally coordinated research effort to study how natural plankton communities respond when seawater alkalinity is actually increased. So similar to ocean alkalinity enhancement, right? And this global project, shortly OAE-PEEP, we're about 17 research groups participating. And we are distributed actually in all continents, which is a really great effort on this side. And each participating research group conducts basically the same experiment in their own local environments, following a common protocol, right? And so the project, what we use is a standardized microcosm unit, which is a 60-liter seawater tank, simply. That encloses a natural plankton community. And each group basically adds the same amount of alkalinity under controlled conditions and then measures the same suite of responses in plankton and in seawater. So it's really an experiment that is tackling the ecological aspect of OAE. And the idea is that these individual studies, once we are all done, can later be combined into sort of a global synthesis that we hope that can hopefully reveal patterns that are consistent across different regions or even across different plankton communities. And this is especially important because we are moving away from relying on single experiments in in one place, isolated in one location. And apart from the fact that it's meant to build the scientific consensus about the potential ecological impacts of OAE, because the experiments are relatively cheap and they're also very simple. The project is also trying to basically promote participation from scientists worldwide by also building expertise and supporting inclusive research from diverse economic backgrounds or even geographical backgrounds in places where OAE research has not actually started yet. So, for example, as you alluded to that, Anna, I'm currently in Kenya to conduct this experiment with colleagues from the Marine Institute here in Kenya. And it's very exciting because I also get to transfer the knowledge, but also we help to establish a new area of research here with the hope that, once I leave, they are able to tailor their own OAE research to locally important questions on the applicability of OAE for example, African waters, which is a very big open question currently. So OAE PEEP it's really an amazing research effort that tries to bring together all the scientists to understand ecological aspects of OAE. Yeah.
That's really cool, especially because both Charly and Giulia also alluded to the fact that you learned how important different locations are, right? And that the reactions or impacts can vary quite significantly in different places. So very, very cool to hear that this is an experiment that tries to sort of find the underlying joint drivers. Do you see other areas where such tangible, scalable, and accessible experiments could play a role in your research next or across the field of OAE generally?
Yeah, so as much as OAE PEEP is really related to OAE, I think it's also creating a template for how we can actually rapidly assess emerging technologies and environmental changes in the ocean before we can actually deploy at scale. And that's actually the kind of proactive science that we need at this moment, because it's really powerful for tackling globally relevant environmental questions. So the most obvious extension of such a such model of experiments would be, for example, I can think of using the same model to other marine CDR approaches, so other carbon dioxide removal approaches that are actually still in their early stages. I think we would all benefit from having such globally coordinated research efforts to actually speed up our understanding. We can also use this, and I think it's something that we need to start thinking about, is looking at combined stresses. And that's because OAE, it will not happen in isolation, or it will not even, in some cases, it might not be deployed in a pristine ocean. Because climate change is still ongoing. And so there's a regulatory need or relevance. Therefore, if we're making decisions about OA deployment, regulators would need to know, will this be safe in a warming or acidifying ocean? And not just, is it safe today in controlled lab conditions, right? So we need to test interventions under conditions that they'll actually face, and that is a changing, stressed ocean. So I think such globally coordinated efforts would be good to integrate other stressors to create some kind of ecosystem predictive capacity, so to say, for real-world applications of marine carbon dioxide removal technologies.
Yeah, that's really interesting, and yet another layer of complication, of course, but I think a really important aspect of this. You're all spread across institutions and disciplines. How do you make sure that results from one group within the consortium actually reach and influence what others are doing? And do you have any concrete examples of that?
Maybe I can reply to that. And maybe the others can say also something else. I think that the Mesocosm experiments are really one of the places where we discuss the most, because you have to consider that during this experiment, we are around, 40 people between technicians, scientists, students that are helping us. I think that Anna, you've been there last year in Kiel, and you've seen that, it's really a big group of people working together. And because we spend so much time in the lab and outside, it's a perfect moment where we can discuss the data, and we can maybe, reply to some of the questions, because there are people which are expert in carbonate chemistry, and I can ask a question about it, and vice versa. So it's really the moment where we kind of discuss the most and decide the most. And also, we use the expertise of each other to also design our experiment. We were talking actually yesterday about these podcasts, and we were and Leila was mentioning that she remember when we were in Helgoland during an experiment a few years ago. And we designed our experiment after some tests that a PhD student from Hamburg University, so from Charly group, he did some tests on the carbonate chemistry. He found out some threshold values for precipitation. And then we discussed about it. And then we design our experiment. So I think that, of course, it's not only during Mesocosm experiment, but this is really the time where different expertise are coming together, and we are able to find the time to decide how to proceed and what is needed in the consortium. And everyone can participate, because there are longer experiments and there's room for everyone to reply to their own questions. So this is a good example.
Yeah, and actually, what was funny, in my case as well, is that I actually joined the first Mesocosm in 2022 in Bergen, where I was still a PhD student in Australia at the time. Didn't know anything about, I've never been to Germany before and never been to Norway before. So that was kind of a first for me. I had to learn to communicate in German with a couple of colleagues from the Guillaume, which was fun. And it actually opened a lot of opportunities, work-wise, because I actually met my current boss there. And that's how I got to exchange with them, and we got to design all the way that we're doing now. On top of that, given that Giulia, Leila, and I are technically neighbors, because we're 45 minutes, an hour away. Of course, we discussed data, but also it opened a lot of doors for friendship in our case. And that was quite nice to have that kind of opportunity to be able to, and that proximity. And it's true, like Giulia was saying, that you have so many brains in such a confined area that, I mean, it is exhausting. It is not denying that, the days are not counted in hours, but just in T1, T2, T3 after addition. So there's no even concept of hours anymore. But it really leads to very proactive research and actually really good conversation and really good ideas that come out of it.
Perfect commercial for going into science and doing field research.
And Charly, are you Germanized now? You're saying T because it's tag, not day,
Yeah, no, yeah.
T1, T2, T3.
No, time point 1, time point 2. Oh.
No. This is tag.
Well, I want to wrap it up and close out the episode a bit by talking about the future and how you're adapting your research to potentially a lot of the real world activity that's ramping up around OAE. I mean, you already alluded to, of course, you have that feedback loop within your own consortia, but I'm curious how you think about the value proposition and the speed at which I'm sure people are craving to receive your results also as you see the activity in the real world unfolding. And maybe that's a question for each of you probably.
Yeah, I can also jump in, and I think that's a really important aspect that you bring, because the pace of real world OA interest is definitely going really fast, and we also want our research to stay relevant, but also useful, right? As that happens, and so one way is that we're paying a lot of attention to, for example, discussions on the type of minerals, all the alkaline materials that are actually in discussion to be used, for example, and this is important from an ecological perspective, but also from an efficiency perspective in terms of Charly's work, because these alkali sources they're alkaline mineral sources. They're associated with their own set of other conditions that have, on one hand, ecological relevance, but also efficiency, right? And then the other aspect is we try to stay very much connected with the broader OAE community. So projects like OAE PEEP or even Ocean Alkalign, where we have, so to say, monthly meetings, for example, they also help us align our experiments with actually what is being discussed or tested in field pilot studies, for example. And that way, the data that we produce are not just academically interesting, but they also directly inform environmental risk assessments, for example, from a regulatory perspective, or monitoring aspects and things like best practices for responsible OAE research. So in short, I think we try to adapt by keeping our experiments realistic, by testing relevant materials and conditions and making sure that our work feeds directly into the global conversation about safety and effectiveness. Yeah.
Yeah, and it's quite interesting to have seen the shift, like we were discussing. It started kind of with modeling, and then a couple of experiments that started with olivine-rich materials like Junite and so on, in very specific experimental design that shifted towards different materials, calcium hydroxide, magnesium hydroxide. Lately, there's been a little bit of a focus on industry byproducts as well, steel slag and kiln dust. So there's been a lot of shift, and this shift is happening. I don't know how much it would have happened in other contexts, but it's true that in the context of OA, it changes very fast. It is undeniably a sexy topic as of now. So a lot of people are putting a lot of energy, a lot of effort into it. So it brings a lot of research and a lot of focus. So it's quite interesting to see how the momentum is shifting every year, essentially, from this type of material to that type of material to this type of phytoplankton and that type of zooplankton. And now we're even discussing, there's been recently a couple of field trials by colleagues of the Carbon Sea Initiative. So it's really nice to see such a shift in that whole research. And it's quite encouraging in the way that, you have really smart brains sitting together on one great solution, or at least one great approach, which is quite interesting to see.
Okay, well, alluded to that. One last question from each of you. I'm curious to hear your sort of go-to favorite R&D question that you really hope to see answered next. Either your personal one or have someone else answer it.
maybe I'll try to link it directly to the ecological aspect, because I think this is something that we don't talk about often. And I think we need better frameworks for risk assessment, and also defining acceptable impact thresholds from an ecological perspective. This is because, I mean, we need to know how much ecological change is actually acceptable, for how much carbon that has been removed, right? And who decides that? We need to develop these frameworks, I think, in partnership with stakeholders, or things like indigenous communities and the broader public. And I think when we start understanding how these frameworks can actually help, I think science can inform a lot of decisions, better decisions for society. But it definitely, we know that science cannot make those decisions alone. So we need a community to actually help us figure out these frameworks for risk assessment. And I would like to see that, more R&D going into those frameworks. Yeah.
And if I maybe add to that, I mean, there's MRV, monitoring, reporting, and verification. It's quite a complicated topic already, but I would like to see a E in front of that. So like to consider also the environmental impact into that. It is, I think it's a direction of many discussions, but I think it's also quite important to consider. I mean, I don't think it's quite important. It is fundamental to consider that.
And do you want to elaborate shortly on that? Do you mean more specific targeted monitoring prescriptions or requirements that are sort of bespoke to certain pathways? Or
No, definitely that. Yeah, exactly.
That sort of go beyond what is currently required.
Yeah.
I mean, and as a follow-up, I think like the MRV is also quite, I mean, it is undeniably a tricky topic given the changing states of the ocean and how much of a difference it can make from, day to night already in terms of measuring CO2 and so on. In my case, because I'm more of a lab person, like we do have, you have to spend, when we talk about carbon and chemistry, we take the time to take a sample a certain way, to have a measurement that is then really good, but it's something that is really involved. And we don't have the kind of the instrumentation to have a quick and easy measurement that is highly reliable or that can pick those small differences that we want to work with. So I think that R&D part has to come into play. I think as of now, we can probably, like Leila mentioned, like it would be nice to have everyone on the same page and agree like on the same approach so that everyone does exactly the same thing in terms of measurements. At least the M part of the MRVE is out, so that's one big thing out. We all agree on the same approach. We'll agree on the same number. Everything is intercomparable, and the rests can come. But yeah, unfortunately, like if we had the chance to have like super high quality instrument that can measure things that we already struggle in a controlled environments, then we could probably more easily do that MRV task, I reckon.
I think there's also the challenge of, from the opposite angle or direction, to identify the potential parameters that maybe do not require the very expensive, like highly accurate, highly detailed measurements that you just described. If there is a sort of agreed upon tested approach, if there is agreed upon sort of list of proxy parameters or so, where you then know if, a change occurs, you have to look deeper into the system. But that link, I agree, is something that is a real challenge and something to look forward to or look into.
Yeah, what I've always wondered, correct me, Giulia and Leila, if I say something wrong, but, we talk about alkalinity, but realistically, the alkalinity is just a concept. It doesn't really does anything to living organism per se. It's rather what comes with alkalinity addition. So, which is why when we talk about equilibrated approach, well, surprisingly, there's little effect because the real part that would become problematic for living organism is this change in pH, this change in CO2. And so I could even consider, not measuring alkalinity at all and just focusing on that pH and CO2.
Which would be great for the environmental aspect, right? But then for the efficiency, something. Yeah, we have to measure many things. We could probably go on for a long time. We just got to the good part, which is MRV.
It's a magic word.
Yeah, well, that seems like a good place for us to wrap it up. Leila, Giulia, and Charly, thank you very much for this incredibly detailed sort of disquisition of your work.
Yeah, thanks for the time, guys. Looking forward to our next meeting. And yeah, good luck with the rest.
Thanks so much for having us. It was very, very fun.
Thanks as well from me. It has been really, really great.
Thanks to our listeners. If you enjoyed this episode, please leave a comment or a review and share this episode with others. If you want to suggest a specific topic for a future episode, please feel free to reach out to us through LinkedIn or via our email address, planc@carbon2sea.org. And with that, we say thank you and hear you next time. Goodbye, all.